G'day, in this video we are going to be covering the basics of electricity and having a look at recapping Ohm's law. So this video covers the first content that appears in inquiry question 2 of module 4. Here we're starting to look at the processes of the transfer and transformation of energy that occur in electric circuits. These two dot points are concerned with the flow of electric current, as well as unpacking Ohm's law in a little bit more detail. In particular, we're going to be looking at scenarios where Ohm's law is obeyed and when we have non-ohmic resistors which do not obey Ohm's law. So our aims for today are to set ourselves up so that we can complete some simple pracs concerned with electricity and Ohm's law. In order to do that, we're first going to define current and the direction that current goes in. The rules associated with direction of current, again, are going to be a little bit counterintuitive, similar to how we've talked about polarity in situations for electrostatics. And also begin to unpack what it takes to either obey Ohm's law or not obey Ohm's law, so that when we actually look at some examples in class, we can unpack that a little bit further. So first off, current. It has a quantitative definition in your data sheet that I is equal to Q on T. I being current, Q being charge, and T being time. In other words, current is a measurement of how much charge can pass a point in a set period of time. Potentially before, you may have heard current be described as the number of electrons which pass a point in a second. And in some ways that's true, but that's not reflective of our unit of measurement, the ampere. The ampere is a measurement of coulombs per second. So in other words, how many coulombs of charge pass in a second. Furthermore, what this also means is we can be measuring current for positive charge, not just for electrons that we see in electrical circuits. And by definition, similar to other definitions, it's all based on how a positive charge would behave. So the definition for current is that current flows in the direction that positive charge would flow, in other words, in direction of the field lines. This means that electrons in a wire actually flow in the opposite direction to current. I'm going to show you what that looks like by adding in two diagrams to show this phenomenon. So in this first diagram, I have essentially drawn up a sodium chloride solution, water which is filled with sodium and chlorine ions. And in this container with salt solution, we have two electrodes, one that's positive, one that's negative, providing potential and an electric field. This potential in the solution will cause the sodium to be repelled by the positive electrode and attracted to the negative. And the chlorine ions will be repelled by the negative electrode and attracted towards the positive. However, based on our definition of current, we would define current as traveling from the left to the right, as this matches the direction that the positive charge sodium will flow in. In the second diagram, I've drawn some electrons in a wire, and if the current is moving from left to right, then the electrons will move from right to left because, again, they move in the opposite direction of current. With a clear definition of current, I now want to look at Ohm's law, V equals IR, an equation you would have seen in years 9 and 10. Ohm's law relates three different variables: current, the flow of charge, or by a more quantitative definition, the amount of charge which passes a point in a particular time. V, which is voltage, this is our potential difference. We've been covering that a fair amount in our electrostatics. When we're talking about potential difference, what this describes is how much potential energy will change per unit charge. And then we have resistance, which relates the current and voltage which exists as electric charge moves through a component in a circuit. Current, as acknowledged before, is measured in amperes and has a capital A for the units of measurement. V, voltage, as we've talked about before, is measured in volts and has capital V as its units of measurement. Resistance could be measured in volts per ampere. That is what it would be by definition if we were to rearrange Ohm's law so that resistance was the subject. That would be R is equal to V on I, so volts per amp. However, usually we use the symbol omega, which stands for ohms, as a unit of measurement for resistance. Current is generally measured with an ammeter and voltage is generally measured with a voltmeter. Technically, you can use a multimeter to measure resistance. You may also come across something called an ohm meter at times, which can measure resistance in a component, but it's not something that we're really going to be using in the scope of this course. When we do use ammeters and voltmeters or multimeters, which are able to measure amps and volts, if we are measuring current in amps, then the meter needs to be connected in series. And if we are measuring volts in any experiment, we need to be connecting the meter in parallel. When we get into class and start doing some practicals, we will apply our knowledge around Ohm's law a little bit further. Some additional information that will be helpful to set you up for these practicals is to reflect on ohmic and non-ohmic devices. If a component in a circuit is described as ohmic, what this means is it obeys Ohm's law. And if we were to plot the current that runs through an electrical component as we increase voltage, we should find that there is a linear relationship. However, some devices are described as non-ohmic, which means as we increase the voltage on a component in a circuit, the current that's able to flow through will not follow a linear pattern, thus being a non-ohmic device because it does not obey Ohm's law. The last thing that I'm going to do in this lesson is show you a little bit of a proof as to why we should see a linear relationship between voltage and the resulting current if a device is considered to be ohmic, obeying Ohm's law. So as we know, for Ohm's law, V is equal to I R. And to rearrange to make R the subject, that would mean that R is equal to V on I. When reflecting on the graph on the left and analyzing the linear relationship that's present, we can have a look at the gradient present, rise over run, and attempt to relate this gradient to Ohm's law. So for this graph, the rise would be equivalent to some sort of current or current change, and the run would be equivalent to voltage or potential difference or change in that potential difference. Note here that these two fractions that we have are the reciprocals of each other. What that means is I can combine both statements to relate resistance and the gradient. What should happen here is that resistance is equal to 1 over the gradient, which is V over I. Similarly, we could write a statement about the gradient, that the gradient is equal to 1 over the resistance. What that means is if we have a device or an electrical component in a circuit which is classified as ohmic, it should follow this rule here, that the gradient between voltage and current should be equal to 1 on R. If this rule is not obeyed and we graph voltage versus current for a particular component, and we do not get a linear relationship, then we can describe that component as non-ohmic. In the experiments we complete in class, what we'll be looking to do is measure the current that flows through particular devices at different voltages, plot the points, and see whether or not we have an ohmic or a non-ohmic relationship. We will also hopefully be able to get into discussing why that is. Thank you very much, everyone. In the next video, we're going to be looking at electricity and relating it to the concept of electrical energy and the work that electricity can do. But until then, have a good one.